Okay, so we talked about restructuring, and now I'm going to give two examples. I'm going to give one example of restructuring of an ill-defined problem, and then I'm going to talk about restructuring of a well-defined problem. So, first, I'll say that restructuring a problem can lead to innovation and technological advances. And so, in a sense, you can think of restructuring as breaking out of an old tradition or an old way of doing things. And so this picture right here, this is a movie called Moneyball. It's based on a true story, and it's this guy right here is Billy Beane, as played by Bill Brad Pitt, and he's the general manager of the Oakland A's. And he has a problem, which is that he just lost his star player, Giambi, and he doesn't have any money to recruit a replacement for Giambi. And so in a meeting with a bunch of scouts or baseball scouts for the team. They're trying to assemble a good baseball team, but they don't have the kind of money that Yankees have, and they just lost three of their best players. And Billy Beane in the scene tells the scouts that they're not really aware of the problem, of what the problem is, and asks one of the scouts what the problem is. The recruiter says that we need to replace three key players. Billy Beane says that that is not the problem. He states that their star player is irreplaceable, and even if he wasn't, they couldn't afford his replacement. And so, according to the recruiters, the problem is that they need to replace their star baseball player. But according to Billy Beane, this isn't even an option to them, and that really the problem is that they're competing with teams that have more money than they do. And by restructuring the problem this way, he realizes that he can't solve the problem in the same way that richer teams do. He has to get more creative. And so at some point, he meets an economist from Yale, played by Jonah Hill. And Jonah Hill is applying statistics or sabermetrics to baseball in order to identify undervalued players that he could use to hire them below market value. Jonah Hill's character mentions that recruiters pay attention to the wrong things, and that one way or one important way to value a player is by focusing on their on base percentages or how often they get on base. And so in a later meeting, Billy Beane says that he doesn't in a later meeting with the recruits. Uh, Billy Beane says that he doesn't like any of the players that the recruits are bringing up, and says that they're all trying to replace Giambi. Uh, and the problem is that they can't replace Giambi. So Billy Beane says that they must create his on base percentage in the aggregate by getting three players that would average Giambi's on base percentage. And so what Billy Beane did was he restructured the problem from trying to replace Giambi with little money to recreating his performance in the aggregate by recruiting three undervalued players. And yeah, and so that's one example. And I'm sure that this is restructuring has led to innovation in other kinds of ways, but this is the one that I'm aware of. So this is an example of where restructuring can profitably be used in an ill-defined problem, but restructuring can also be used to profitably in more well-defined problems. So now we'll look at this. We'll take one example. Okay, so this is called the trains and fly problem. And what it is you have two trains that are 100 miles apart, and they're traveling towards each other at 20 miles per hour. And at one of the trains, there's a fly, and the fly can travel 40 miles per hour. Okay. And the question is, if the fly flew to the other train and then instantaneously turned around and flew back to the other train and then turned around and did the same thing over and over again, uh, how many miles would the fly have traveled um, before the two trains collided, right? So I'm going to go into some math. I'm going to solve the problem. I'm going to solve the problem in a computationally intensive way. And just to be clear, you don't have to understand the math fully. You just have to understand the surface level, why it's a computationally complex solution. And so the way you solve this is you go, okay, well, the combined uh, speed of this fly and this train is 20 plus 40, which is 60 miles per hour. And so for distance one, for this one distance, right, you go 100 divided by 60 times 40 miles per hour, and that equals 66.67. Okay. So that's only the distance one. What about when the fly turns around, right? Well, there you go. Now, what you do is the same thing that you did before, except now your new distance is not 100, but 33.3. And you can see that if you do this multiple times, you do this over and over again, what happens is you get 200 times, in parentheses, one third plus one third squared plus one third to the third, so on and so forth. And if you add all of those distances up, you get 100 miles per hour. Okay. And again, if you don't understand the math, don't worry about it. The point is that you have to compute each distance that the fly travels, right? So when the fly travels this way, you have to figure out what that distance is, and then when the fly turns around and goes back to the other distance, you have to figure that one out, so on and so forth, which is a computationally intensive solution. However, the more computationally clever, more efficient solution is you realize that the combined speed of the trains is 40 miles per hour, and that the trains will meet in 100 divided by 40, 2.5 hours, right? And so then the fly, right, travels 2.5 hours at 40 miles per hour, which gives you 100 miles per hour. So this is a computationally more efficient solution. And here's this guy named John von Neumann. He was a mathematician in the post-war World War II era. And John von Neumann was asked this question at a conference or something about the ball, about the flies and the fly and the trains, and he replied immediately with the correct answer. The questionnaire was disappointed and said something like, "Oh, you must know the trick to solving this." Von Neumann replied, "What trick? I just summed up the infinite series," right? Which is what he basically is saying. I just did the computationally complex solution. And so, yeah, of course, the reason why this is funny and remarkable is because most people would need much more time to solve it in this computationally complicated way. But John von Neumann had exceptional ability for computation, and he was known for this, and so he was able to do it. And so the point of this story is to illustrate that most humans do not have the capacity for such computational ability, and therefore we must find more efficient ways to solve many problems like these. It is often the case that a more efficient solution exists, but that in order to realize it, you must restructure the problem. In other words, you must reorganize the problem so that it's represented differently than how it's presented. Okay, in the next video, we'll talk about the Monty Hall problem. And yeah.